Hi, this video is about waves and wave properties. Waves we can define as an organized disturbance that travels with a well-defined speed. So it's some kind of disturbance in the medium that it's in, and it travels with a well-defined speed. A mechanical wave, that requires a medium. Now, a medium is not some kind of psychic. In this case, the medium just means that's the physical material that's being disturbed or oscillated. So, for example, a water wave, as would appear on the ocean or on the top of a cup of coffee, if you blow on it, the medium is the water that's oscillating. And a sound wave that you're hearing right now, it's the air that's oscillating. So the air would be the medium in that case. Not all waves are mechanical, but we can classify all waves into two types. And so the first type is typically what I think of when I think of a wave, and that's a transverse wave. So if you remember from geometry, a transversal is a line that crosses another line. And so a transverse wave is when the medium vibrates perpendicularly, that's a big word, perpendicularly, to the direction of the wave velocity. So a water wave is a pretty good example of a transverse wave. The water wave goes up and down, goes up and down, and the wave goes sideways. So, or you can shake a string up and down or a rope up and down. The rope goes up and down, but the wave energy goes at a direction perpendicular to that. So I listed three here for examples of transverse waves. Shaking a string up and down. Water wave is a pretty good transverse wave. And then light. In fact, every electromagnetic wave, which we'll talk about at the end of this unit, is a transverse wave. The medium there is the electric and the magnetic field. The other type of wave is a longitudinal wave. Sometimes it's called a compressional wave, but it's called a longitudinal wave. And that's when the medium vibrates along the direction of wave velocity. So instead of going perpendicular to the wave velocity, it vibrates parallel or along the direction. I like to use the word along because it correlates with the name, right? Longitudinal, the medium vibrates along the direction that the wave moves. So a good example of that is if you take a big slinky and you compress it and then release that compressional pulse will travel down the length of the slinky. So a compressed slinky and sound waves are our other prime example of longitudinal waves. So remind me to see some demos of those in the classroom when you come back the next day. All waves, though, whether they're transverse or longitudinal, have the same types of properties. And so I've listed a couple things here, but take a moment and sketch this wave here, right? I did the axes and then I drew kind of up and down and then up and down again. There and back, just like Bilbo Baggins. And so the top parts of the waves are called crests, and the bottom parts are called troughs. So the highest point is a crest and the lowest point is a trough. The distance from this midpoint to the top, or from the midpoint to the bottom, that's called the amplitude of the wave. So technically it's the maximum displacement from equilibrium. It's measured in meters. You'd have to have some kind of information about how tall that wave was and measure it. For mechanical waves anyway, it'd be measured in meters. So that's the amplitude. What's amplitude correlated with? Well, if it's a sound wave, amplitude's correlated with loudness. So loud sounds have very high amplitudes. Another property is wavelength, and that's the distance that the wave travels in one complete cycle. In other words, from crest to crest, that would be one wavelength. So that's the distance the wave travels in one complete cycle. The symbol for wavelength, though, is a Greek letter. It's a lowercase lambda, which looks sort of like an upside down Y, I guess. Some people think it looks like an X, but it's missing the top part there. I like to think it looks like a brontosaurus. But anyway, that's the symbol for wavelength, and it's measured in meters too. So you could literally take your ruler if you wanted and measure from crest to crest and figure out what the wavelength is. A few more properties of waves, of all kinds of waves. One is the period, and that's the time for one complete cycle, one complete oscillation, there and back again. And that's measured in seconds. So the abbreviation is a capital T because we've used lowercase t before for kind of a generic time, but this is a specific time. This is the time for one cycle. So we use a capital T, uppercase, but it's measured in seconds. So this is literally time per cycle, right? That's how to think about it. Period is time per cycle. The reciprocal of that is frequency. So frequency is the number of cycles in a certain time. And so that time is usually per second. And so the standard unit for frequency is a cycle per second. And that has a name. We named it after Heinrich Hertz. So we abbreviate it HZ, right, for Hertz. And you've probably seen that before on your radio dial. The station might be 800 kilohertz or 95.5 megahertz, something like that, or in computer clock speeds and whatnot. So that's called frequency. If we're talking about a sound wave, the frequency would be correlated with the pitch of the sound wave. So high pitched, high frequency, low pitched, low frequency is the idea. And frequency in period, T and F, little f for frequency, use capital F for forces, so little f for frequency, and capital T for period, they're reciprocals of one another. So these are two equations you can put on your cards. F is 1 over T and T is 1 over F. So period is time per cycle and frequency is cycle per time. So they're just reciprocal. So if the period is half a second, it takes half a second for the wave to go up and down and back to where it started, then the frequency is 1 over 0.5, which is 2 cycles per second, so 2 hertz. The last property is wave speed. And it's exactly what you think it is. It's the speed at which the wave travels. So speed is distance over time. And for a wave, the distance is the wavelength. That's the distance it travels in one cycle. And the time for one cycle is the period. So the equation for wave speed is lambda divided by t. That's wavelength divided by period. And I would put that on my toolbox as well. And go ahead and write down what all the symbols mean so you don't forget that. Put that on the card as well. And since 1 over the period is the same as the frequency, then instead of writing it like this, we could substitute in for f and write it like this. So wave speed is also frequency times wavelength, f times lambda. So if a sound wave has a frequency of 256 hertz, which by the way is middle C, and it has a wavelength of 1.34 meters, what's the speed of sound? I listed my givens and my unknown. I wrote the equation, v equals f lambda. I substituted and I saw. So the speed of sound is about 343 meters per second. And that's the speed of sound in air at kind of an average room temperature. And last, it would be helpful, I think, for you when you're working in class the next day on this stuff, if you have all these things ready at hand to you. So I kind of summarized them here in a nice table. Here's the wave property, the symbol that you'll see for it, the abbreviation, and then the standard unit over here on the right. All right, thanks for watching.